Alright, so this was the last problem that we solved yesterday. Okay, let us proceed. So let's see this next problem. Let's see this one. When a metallic surface is illuminated with radiation of wavelength lambda, the stopping potential is V. If same surface is illuminated with radiation of wavelength 2 lambda, the stopping potential is V by 4. The threshold wavelength of the metallic surface is. So problem is simple, right? Alright, tell me. When a metallic surface is illuminated with radiation of wavelength lambda, stopping potential is V. Okay, so we can write that E times V would be equal to what? It's equal to Hc by lambda, because it is illuminated by wavelength lambda, okay, minus phi naught. And then if same surface is illuminated with radiation of wavelength 2 lambda, the stopping potential becomes V by 4. So this is the first case. Second case, we can write that stopping potential becomes V by 4. So E times V by 4 is equal to Hc by 2 lambda minus phi naught. Right, this is your equation 2. Okay. Then what we can do is we can substitute this equation 1 into 2, or we can solve them simultaneously. Both things are identical. So let's substitute 1 into 2. So if we do that and take this 4 on this side, okay, so I will take that 4 on this side, 4 times Hc by 2 lambda minus phi naught, and what remains on this side is, okay, EV only, and that is Hc by lambda minus phi naught. Okay, and what we want is the threshold wavelength. So first let's find out what is phi naught, and then we'll get the threshold wavelength. So just multiply this out. So what do we get? So this is 4 times Hc by 2 lambda, that means 2 Hc by lambda minus 4 pi naught. Okay, and this is Hc by lambda minus pi naught. So if we move this thing on this side, that is plus 4 pi naught minus pi naught, that would be 3 pi naught. So 3 pi naught is equal to, this is 2 Hc by lambda, and this Hc by lambda, if you move it on that side, it would be equal to Hc by lambda. So Hc by lambda, right? And what is phi naught? So phi naught is, we know it is Hc divided by lambda naught. So 3 Hc divided by lambda naught is Hc by lambda. So Hc and Hc get cancelled out, and therefore what do we get? We get 3 by lambda naught is equal to lambda, or lambda naught would be equal to what? Take this 3 on that side, it would be equal to 3 lambda, right? This 3 will go in denominator. Okay, 1 by lambda naught is 1 by 3 lambda, that means lambda naught is equal to 3 lambda. So that is option B. Okay, this is clear. Okay, let's see next one. A photoelectric surface is illuminated successively by monochromatic light of wavelength lambda and lambda by 2. Okay, so first we use wavelength lambda, then lambda by 2. If the maximum kinetic energy of emitted photoelectrons in the second case is 3 times that the first case, the work function of the surface of the material is. So again, this is simple. This is simpler than the last one, right? So first you use wavelength lambda, okay, and then lambda by 2. So maximum kinetic energy in the second case is 3 times. In second case is 3 times that of the first case. So you can say Ke1 is equal to what? Hc by lambda minus work function phi naught. In second case, it is Ke2 is Hc by lambda by 2 minus phi naught, right? We are just writing down the Einstein's equation, and this 2 will go in numerator, and this thing can be written as what? Ke2, it's given to be equal to what? 3 times of Ke1. So it is 3 times of Ke1 is equal to 2 times of Hc by lambda minus phi naught. And then you can substitute this Ke1 here. Okay, so substitute ke1 here. What's ke1? It is hc by lambda. Then you have 3 times of that. 3 times of hc by lambda minus phi naught is equal to 2hc by lambda minus phi naught, right? So then multiply this out. So what do you get? Therefore 3hc by lambda minus 3 phi naught is equal to 2hc by lambda minus phi naught, and then just move this thing on this side and this thing on this side. Okay, so we'll get the answer. So 3hc by lambda minus 2hc by lambda is just hc by lambda, and that is equal to 3 phi naught minus phi naught means 2 phi naught, right? 2 phi naught is equal to hc by lambda, and therefore what is phi naught? Phi naught is just equal to hc divided by 2 lambda. Okay, so again a simple problem. Let's see next one. A certain metallic surface is illuminated with monochromatic light of wavelength lambda. The stopping potential for the photoelectric current for this light is 3V0. Stopping potential is 3V0. If the same surface is illuminated with wavelength 2 lambda, the stopping potential is V0. The threshold wavelength for this surface for photoelectric effect is. Okay, so first it is illuminated with the monochromatic light of wavelength lambda. Stopping potential is given to be 3V0. So for first case, so in these kind of problems we just need to write down the Einstein's photoelectric equation. So for the first case, stopping potential is what? 3V0. So you can say E times 3V0 is equal to what? Hc by lambda minus phi naught. Okay, but don't write hc by lambda naught at the beginning only. Okay, just write phi naught. Then the stopping potential is 3V0. The same surface is illuminated with wavelength 2 lambda. Okay, the stopping potential is V0. So again, then if same surface is illuminated with 2 lambda, stopping potential becomes V0. So E times V0 is equal to Hc divided by 2 lambda minus phi naught, right? Okay, so this is first equation, this is second equation, and then what you can do here is, now you can substitute second into the first one. Okay, you can substitute second into first one, right? Or you can simultaneously solve these equations. I mean, multiply the second equation with 3, then subtract that equation from the first one. So it is identical, right? Okay, so let's substitute this. So what do you get? So this is 3 times of, okay, E V0, E times V0, and what's that? Hc by 2 lambda minus phi naught. So Hc by 2 lambda minus phi naught, and that's equal to Hc by lambda minus phi naught, right? So then you want threshold wavelength, that's why you are doing this. Okay, so then this is 3 times Hc by 2 lambda, 3 times Hc by 2 lambda minus 3 phi naught, and that's equal to Hc by lambda minus phi naught. Okay, so then take this on this side, so it will be 3 phi naught plus, okay, it will be positive, so 3 phi naught minus phi naught is 2 phi naught, and take Hc by lambda on that side. So what do you get? So it is 3 times Hc by 2 lambda, 3 by 2 Hc by lambda minus Hc by lambda is equal to 2 phi naught, right? If you move this thing on this side, it becomes 2 phi naught. Okay, and this is 3 by 2 minus 1, so that's 1 by 2. 1 by 2 Hc by lambda is equal to 2 phi naught. 2 phi naught is equal to 1 by 2 Hc by lambda, and then you can just write phi naught as, okay, let's write phi naught as hc divided by lambda naught and move this 2 on that side. So that is equal to hc divided by 2 times 2 means 4 lambda. So hc gets cancelled out. So lambda naught is equal to 4 lambda. That's the answer. Option D. Lambda naught is equal to 4 lambda. Right? It is option D. Let's see next one. When the energy of incident radiation is increased by 20%, okay, the kinetic energy of photoelectrons emitted from a metal surface is increased from this value to this value. So 0.5 eV to 0.8 eV. The work function of the metal is, right, so we want work function in eV only. Okay, so then, so suppose you have first case when kinetic energy when the energy of incident radiation is E, let's call it E only. So then you have Ke1 is equal to E minus phi naught. Okay, then it is increased by 20%. So if it is increased by 20%, then what would be the value of E? So I can say E prime would be equal to what? 20% extra. So 120% of E, right? That is 120% means 1.2 times of E. Okay, yes, no. Or what I can say is E by E prime would be equal to 100 divided by 20% extra, so 120. Okay, and if you solve this, then this is take E prime on this side and divide the denominator by 100, so it will become what? 1.2. So move that 1.2 on this side, so you get E prime is equal to what? 1.2 times of E. Okay, so then what happens? You get Ke2 is equal to E prime minus phi naught. Okay, and what is E prime? It is 1.2 times of E minus phi naught. This is Ke2. Ke2. Okay, then what we can do here is, so you can move this phi naught on this side, okay, and substitute that here, or we can multiply this equation with 1.2, right? We can multiply the equation with 1.2 and then subtract the second equation from the first one. Okay, both ways are identical. So let's multiply this one with 1.2, first equation with 1.2. So this thing multiplied with 1.2 and write it down here. So what do I get? 1.2 times of Ke1. Okay, we'll substitute the values, is equal to 1.2 times of E minus 1.2 times of phi naught. Okay, so we have this equation. Ke2 is equal to 1.2 times of E minus phi naught. Okay, and Ke1 is equal to, you have E minus phi naught, so E minus phi naught. So just multiply this second equation with 1.2. Okay, so what we'll do is we'll write this equation like this, and then I will multiply this whole equation with 1.2, 1.2 and 1.2. Then I will subtract this one, so this will become positive, right? So therefore this thing gets cancelled out, 1.2e and 1.2e. 1.2 times of Ke1, 1.2 times of Ke1 minus of Ke2 is equal to, you have phi naught minus 1.2 times of phi naught, right? You have this equation, then put the values. Okay, so this will become what? Minus 0.2 phi naught is equal to, what is Ke1? So it is 0.5, and what is Ke2? It's 0.8. 1.2 multiplied by 0.5 minus 0.8, and this thing is 1.2 times of 5 is 0.5 is what? It's 0.6. This is 0.6 minus 0.8 is minus 0.2 times of phi naught, and this is minus 0.2, okay, and you have minus 0.2. So if you divide that with this thing, you will get what? Phi naught equals to 1. So I think that should be the answer. Okay, this is correct. Is this correct? Yes, no? Okay, see the next one. For photoelectric emission from certain metal of cutoff frequency is nu. For photoelectric emission photoelectric emission from certain metal, the cutoff frequency is nu if radiation of frequency 2 nu impinges on the metal plate. The maximum possible velocity of the emitted electrons will be, right? So let's see this one. For photoelectric emission from certain metal surface, cutoff frequency is nu. Cutoff frequency is nu. Okay, so this is your nu naught. Nu naught is equal to what? Nu only. And if radiation of frequency 2 nu impinges on the metal plate, okay, so what would be the maximum possible velocity? This is simple. So you have half of m into V max square is equal to what? H times whatever is the frequency, here it's 2 nu, minus h nu naught. But what is nu naught? Nu naught is equal to nu. This is given, right? Cutoff frequency itself is nu. So 2 times h nu minus h nu is just h nu, and that is half of m into V max square. And you want V max, so take that half m on other side. 2 goes to the numerator, so it is 2 times h nu divided by m is V max square. Okay, and therefore what is V max? It is just square root of that, 2 times of h nu divided by m. Okay, so it is option A, right? This is simple. Okay, this is clear? Yes, no? All right, it's very simple. Let us see next one. Two radiations of photons energies 1 electron volt and 2.5 electron volt successively illuminate a photosensitive metallic surface of work function 0.5 electron volts. Ratio of maximum speeds of emitted electrons is, okay, the ratio of maximum speeds of emitted electrons is, right? So now you have first case, half of m V max square is equal to what? It is energy of photon E1 minus phi naught, and in second case you can write it is half of m V max square would be equal to what? E2 minus phi naught, right? So let's say KE1 is equal to E1 minus phi naught. E1 is the energy of photons, and KE2 is equal to E2 minus phi naught. Just divide first with second because you want ratio of maximum speeds, right? So that is equal to what? E1 minus phi naught divided by E2 minus phi naught. So E1 is 1 electron volt, okay, minus phi naught is what? 0.5 electron volt, and E2 is 2.5 electron volts, and again phi naught is 0.5 electron volts, and kinetic energy is proportional to, you have, this is half mv square, so it's proportional to v square, and that's why what you can do is instead of placing writing half of mv square, you can just say it's v1 by v2 square, right? So that's equal to, this is 0.5 divided by 2.5 minus 0.5 is 2. 0.5 divided by 2 is 1 by 4. right? 0.5 divided by 2 is 1 by 4. So if v1 by v2 square is 1 by 4, what is v1 by v2? v1 is to v2 is 1 is to 2. Okay, so it is option B. Let's see next one. The threshold frequency for a photosensitive metal is this much. If the light of frequency 8.2 multiplied by 10 raised to 14 hertz is incident on this metal, the cutoff voltage for the photoelectron emission is nearly. Okay, tell me. Right, so you want cutoff voltage means you need to use this formula. EV0 is equal to what? And frequency is given. Threshold frequency is this much and frequency of light is this much, right? So h nu minus h nu naught. Okay, or h you can take common, it's nu minus nu naught. Just substitute values. So what do you get? This is 6.6 multiplied by 10 raised to minus 34 multiplied by 8.2 multiplied by 10 raised to 14 minus 3.3 into 10 raised to 14, and this is E times V naught. You want cutoff voltage only, so V naught would be equal to, take E also on that side, so E is 1.6 multiplied by 10 raised to minus 19. Okay, so we can solve it roughly. So this thing would give us 4, right? Roughly we can say this thing gives us 4 multiplied by 10 raised to minus 34, and this thing is plus 14, so it is 10 raised to minus 20. Okay, 10 raised to minus 20, and this minus 19, so it gets cancelled out, and what remains is 10 raised to minus 1. Okay, so 10 raised to minus 1, then what remains is 8.2 minus 3.3 will give you what? It's 4.9. Okay, so nearly 5. 5 times 4 is 20. So 20 times 10 raised to minus 1 means 2. Okay, so it's option B. Check my calculation. Okay, tell me. That's correct, right? The potential difference that must be applied to stop the fastest photoelectrons emitted by nickel surface having work function of this much when ultraviolet light of 200 nanometer falls on it must be. Okay, so tell me, again it's similar. So you want the stopping potential, right? So it is E times V naught is equal to, and now what's given? Now what's given is the wavelength. Okay, wavelength is 200 nanometers. So you have hc by lambda minus phi naught. So then put the values. So what is hc? So phi naught is given in electron volts, right? hc we know it is 1240 ev nanometers. Okay, ev nanometers divided by lambda. What's lambda? Lambda is 200 nanometers. Just substitute that. So minus you have work function is 5.01. Okay, and that is E times V naught. So if we divide that, what do we get? 2 points, shift this one. So 12.4 divided by 2 is 6.2. 6.2 minus 5.01. 6.2 minus 5.01. That is just 1.19, or nearly you can say 1.2. Okay, so 1.2, right? So this will give you 1.2 volts, but stopping potential is always negative, right? So EV0 is 1.2, means V0 is equal to what? It gives you V0 is equal to minus 1.2 volts, because 1.2 is present, minus 1.2 is also present, so the answer would be minus 1.2 volts, because stopping potential is always negative, right? So this is very simple. Okay, let's see next one. When photons of energy h nu fall on when photons of energy h nu fall on an aluminum plate of work function E naught, photoelectrons of maximum kinetic energy K are ejected. Okay, if frequency of radiation is doubled, the maximum kinetic energy of ejected photoelectrons will be. So again, this is also simple. So earlier maximum kinetic energy was K, right? And that's equal to what? H nu minus phi naught. And what you do is you double the frequency. Okay, so frequency is doubled, you get K prime is equal to 2 times of H nu minus phi naught, and then there is nothing. Okay, so what we can do is we can just subtract the first equation from the second, right? Because this is 2h nu, this is h nu. So let's subtract. Let's take this equation down and subtract it. So this becomes minus minus plus, and therefore you get K prime minus K is equal to h nu, and this phi naught and phi naught will get cancelled. So take K on that side and you get the answer. So K plus h nu, right? So that is the answer. It's option A. It's very simple, right? Okay, let's see this one. A photosensitive metallic surface has work function h nu naught. If photons of energy 2h nu naught fall on this surface, the electrons come out with maximum velocity of this much. When photon energy is increased to 5h nu naught, then the maximum velocity of photoelectrons will be. Tell me. This is very simple. Yes, what would be the answer? Work function is h nu naught. Photons energy is 2h nu naught first. Then you have some kinetic energy. Ke1 is equal to, you can say 2h nu naught minus work function, that is h nu naught. And then you increase the energy of photons to 5h nu naught. So 5h nu naught minus h nu naught would be equal to Ke2, right? We want to compare the maximum velocities, but let's solve this first. Then we can divide this one with this one. So what do we get? So on left hand side you will have v1 by v2 square, and on right hand side you have, this is first of all h nu naught will get cancelled out, and this is 2 minus 1, so that's 1. 5 minus 1 is 4, so this is 1 by 4. That's it. So you have v2 just equal to what? Take square root of this thing, so that thing is 1 by 2. So that's v1 by v2 is 1 by 2. So v2 is just equal to 2 times of v1. So v2 is just 2 times of v1, and that is equal to, so 2 times of 4 into 10 raised to 4 multiplied by 10 raised to 6 plus 6. So it is 8 multiplied by 10 raised to 6 meters per second. Right, so that's the answer. It's option C. Okay, it's very simple. There is nothing in this question, right? Okay, good. Let's see next one. According to the Einstein's photoelectric equation, the graph between the kinetic energy of photoelectrons ejected and frequency of incident radiation is. Tell me which one is correct. This one, this one, this one, or this one? Option D. Okay, everyone, that was asked twice. Option D. Okay, very good. Right, so Ke is equal to what? It is equal to h times nu minus phi naught. Okay, so for K equals to 0, you have nu equals to what? For K equals to 0, you will have nu equals to put this thing is equal to 0. So h nu minus phi naught is 0. Then h nu is equal to phi naught. So nu is equal to what? Phi naught by h. Okay, or you can just say nu is equal to nu naught. For that, the k is equal to 0. Right? Phi naught by h means it's nu naught only. Okay, so it is some positive value. Okay, so for some positive value of frequency, kinetic energy is 0, and then it will linearly increase. Kinetic energy will linearly increase with the frequency. So that is simple. It's option D. Okay, so before this experiment called photoelectric effect, we used to believe that light is made up of electromagnetic waves. Okay, so see, dual nature of radiation, what's that? So some phenomenon like interference, diffraction, polarization can be explained by wave nature of light. Okay, and in this chapter we have seen in the photoelectric effect, the photoelectric effect cannot be explained using the wave nature of light. You need to think of light as particles or packets of energy, right? Okay, called as photons. But now, is the photon nature sufficient? It is not sufficient. Okay, right? Because using this nature, you cannot explain the interference, diffraction, polarization, etc. And that's why both natures of light, that is the particle nature and the wave nature, are important, equally important. So now our current understanding is that light is, so what is light? So answer to this question depends on what you are using to probe light. Okay, so if your experiment involves interaction with waves, then light will behave like waves, and if your experiment involves interaction with particles, then it will behave like particles. Okay, so light shows both natures, the wave nature as well as particle nature. Okay, right, so this is our current understanding. Now we understand that light shows dual nature, the particle nature as well as wave nature. So then next, let's understand de Broglie hypothesis. Okay, some people call it de Broglie. Okay, but it's not de Broglie, it is de Broglie. So what is de Broglie hypothesis? So then next, let's talk about the matter waves, that is the wave particle duality. Right, wave particle duality. So what's this? So de Broglie was a physicist and he hypothesized, I mean he gave us a hypothesis. So according to de Broglie, the nature is symmetric. If radiation, which was well established wave, can show the particle nature, then there should be no bias. The particles should also be able to show the wave nature, right? If radiations, which are waves, it was established by the Michael Faraday and Maxwell, that light is made up of electromagnetic waves. So if they can show, or not they, if light can show the particle nature, okay, that is waves can show particle nature, then particles like electrons, etc., whatever particles, they also show, okay, according to de Broglie, they also show what? They also show the wave nature. Okay, because nature should be symmetric, there should be no bias. Okay, so he gave us hypothesis, as wave behave like material particles, similarly matter must behave like waves. Okay, and there is a wave associated with a moving particle, and the wavelength of that wave, which is known as, the wave associated with moving particles, is known as matter waves. Okay, matter wave, and its wavelength is given by h by p. Its wavelength is given by what? H is the Planck's constant, p is the p is the momentum. Okay, so lambda is wavelength of matter waves, it is given by h by p. Okay, p is the momentum, right? So now we need to remember this thing. Okay, so where did it come from? So answer to that is, now if you think about Einstein's mass energy relation, so E is equal to mc square. Okay, and you have energy of a photon. So what is energy of photon? So E is equal to hc by hc by lambda is equal to mc square. Okay, then cancel out this c with this one, so you get h by lambda is equal to m times c. So this is nothing but the momentum of photon. Okay, momentum of photon, right? So that is p. So you move it on this side, then what do you get? So lambda, the wavelength of photon, can be written as what? H by p. Okay, wavelength of photon can be written as h by p. So just like this is the relation between wavelength of photon and momentum of photon, right? So just like that, a particle having momentum equal to p must show there must be a wave associated with that particle called as matter wave, and the wavelength of that wave is lambda. Okay, lambda is equal to what? H by p. Right? Is this thing clear, everyone? Okay, good. So now this equation itself shows the dual nature of radiation as well as matter. So momentum, we associate momentum with particles, right? So moving particles have some mass, some velocity, so they have some momentum. Okay, their momentum is what? Mass times velocity. And wavelength is associated with what? It is associated with waves. Okay, so this is connection between the two natures, right? The wave nature and particle nature of matter as well as radiation. Okay, all right. So this equation shows the duality of matter as well as radiation. Okay, all right. So we have lambda equals to h by p. After that, next we have, if a charged particle is accelerated through a potential difference of v, then what would be its wavelength? Okay, so charged particle is accelerated through a potential difference of v, then what would be its wavelength? Okay, what would be the wavelength of matter wave of that particle? So we have kinetic energy of the particle would be equal to what? The potential energy used to charge that particle. Sorry, not to charge the particle. So kinetic energy of particle would be equal to what? Potential energy used to accelerate the particle. Okay, so kinetic energy is p square by 2m, right? It's half of mv square, and it can also be written as p square by 2m. So you have p square by 2m equals to q multiplied by v. Q is the charge on particle, v is the potential difference. Then take that 2m on this side, so you get p is equal to, its momentum is equal to square root of 2m qv. Okay, square root of 2m qv. And then you can easily find out its wavelength. So lambda equals to h by mv, or h by p. And what is p? So it is square root of 2m qv. So you have h divided by square root of 2m qv. Right? So we need to remember this formula. Okay, or otherwise we'll need to find it out if there is a question based upon this. Okay, so better to remember lambda is equal to what? H divided by square root of 2m qv if it is accelerated by potential difference of v. Right, this is clear, everyone? Okay, good. So then there was Davis and Germer experiment. This topic is deleted from the syllabus. Okay, so we'll not talk about that. So now, if electron is accelerated by, see, we'll take this formula, and in place of the mass of particle, we'll put mass of electron. Charge on the particle, will put charge on electron, right? So if electron is accelerated by a potential difference of v, what would be its wavelength? Okay, so its wavelength turns out to be equal to 12.27 divided by root of v angstrom unit. Okay, and this wavelength, by the way, this wavelength is known as de Broglie wavelength. Okay, because this is de Broglie's hypothesis. Okay, this is a de Broglie wavelength. De Broglie wavelength is equal to this thing, lambda is equal to 12.27 divided by root of V angstrom unit. So we just need to remember this formula separately for electrons, okay, because there have been questions based upon this. So lambda is equal to 12.27 divided by root of V angstrom units, right? And by the way, there was an experiment called as Davison-Germer experiment, which confirmed the dual nature of matter, okay. So in this experiment, what they did was, so what was established? So suppose these are electrons coming this way, these are electrons, okay, electrons, they get reflected from here, suppose, okay, from different planes. So then there would be some part difference between electrons, and then what you see here is the diffraction pattern, okay, something like diffraction pattern. So diffraction pattern is reserved to what? Waves only, but electrons also show diffraction pattern, means electrons show wave nature. That's it, okay. So Davison-Germer experiment in nutshell, okay. So it was confirmed by this experiment. All right, let's see this one. The minimum wavelength of X-rays produced by an electron accelerated through a potential difference of V volts is proportional to. Tell me which one is correct. Yeah, option C. Very good. Very simple question, right? Okay, so this was from NEET 2023 only. Let's see next one. An electron is accelerated from rest through a potential difference of V volts. If the de Broglie wavelength of electron is 1.227 multiplied by 10 raised to minus 2 nanometers, the potential difference is. So de Broglie wavelength is given, and we know that lambda is equal to 12.27 angstrom divided by root of V, and wavelength is also given. So let's move this root V on this side. So this is 12.27 multiplied by 10 raised to minus 10. Okay, you got the answer. Good. And lambda is what? 1.227. 1.227 multiplied by 10 raised to minus 2. But that is in nanometers. So multiplied by 10 raised to minus 9. Right. This is 10 raised to minus 11. Okay. This is 10 raised to minus 11. Move that to the numerator, so it becomes 10 raised to plus 11. Plus 11 minus 10 is 10 raised to 10. Okay, so it is like this thing divided by this thing will give you 10, and this is also 10 raised to 1, so this is 100, right? So then root V is 100, so this thing is 10 raised to 4. I'm sorry, V is equal to 10 raised to 4. So that was the answer, Selva Kumar.
Yes, sir.
Okay, so 10 raised to 4 volts, right? This is very simple. Okay, this is from NEET 2020, and the question based on this has been asked many times. Okay, all right, let's see next one. An electron is accelerated through a potential difference of 10,000 volts. Its de Broglie wavelength is, again same. Okay, simple question. This is from NEET 2019. Okay, so NEET 2019, NEET 2020, same question, right? So lambda equals to you have 12.27 multiplied by 10 raised to minus 10, right? Because they have given the powers here. Okay, one answer is in nanometers. Let's check. And it is 10,000 volts, means 10,000 volts means what? 10 raised to 4 only. Okay, so this thing divided by root of 10 raised to 4, so that's 10 raised to 2. 10 raised to 2 in numerator becomes 10 raised to minus 2. 10 raised to minus 10 minus 2, that is 10 raised to minus 12. So it is option C. Okay, so it's 12.2 multiplied by 10 raised to minus 12 meters. Option C. right? Very simple. There is nothing in the question. So the de Broglie wavelength of neutron in thermal equilibrium with heavy water, okay, at temperature T. So now it might be thermal equilibrium with heavy water or anything else, right? But important thing is the temperature is T. Then you can treat a neutron like an atom, okay? Neutron is just like an atom, or if you have hydrogen atom, you remove an electron from it, what remains is a neutron, right? So it's like an atom only, okay? So it will have kinetic energy, that neutron will have kinetic energy. K is equal to what? It's equal to 3 by 2 kBT, okay? Kb is the Boltzmann constant, right? We remember this from kinetic theory of gases, okay? So this neutron is just like an atom, okay? So then kinetic energy can be written as p square by 2m, and that is equal to 3 by 2. Let's write k only for kb, okay? Kt, 2 gets cancelled, move m on that side, so you get p square is equal to 3 times mkt, okay? And then therefore what is p? P is square root of 3 mkt, and therefore you have its de Broglie wavelength lambda equals to h by p, that is h divided by square root of 3 mkt, right? This is clear. It's option A, right? So simple, very simple. Of course, if we know this, okay, good. All right, let's see next one. An electron of mass m and a photon have same energy E. The ratio of de Broglie wavelengths associated with them is, okay? So electrons mass is m and photon, they have same energy, okay? So for a photon, you can say E is equal to what? It is h nu, that is hc by lambda, okay? So let's write this for photon. E is equal to hc by lambda p, okay? This is for photon, right? We have studied this. The ratio of de Broglie wavelengths. So for a photon, E is equal to hc by lambda p. And then for an electron, what do you have? For an electron, electron's energy is also same. So electron's energy, you can write p square by 2m for the electron is equal to, it's equal to what? Its kinetic energy. This is its kinetic energy. E is equal to p square by 2m, okay? And therefore what would be its momentum? So p square is 2me, and so you have p equals to square root of 2me, okay? Then you can easily find its de Broglie wavelength. So lambda of electron would be equal to what? So it is h divided by square root of 2me, right? And what would be lambda of photon? So just move this e on other side. Lambda of photon is equal to hc divided by e, okay? So you want electron to photon or photon to electron? Electron to photon, right? We want ratio of wavelength of electron to wavelength of photon. So just divide this, okay? So then we get lambda of electron divided by lambda for photon is equal to HH will get cancelled, right? Or let's write this religiously. Lambda, sorry, H divided by 2me multiplied by, you have E by HC, okay? So HH will get cancelled, HH will get cancelled, and then you have HE by HP, sorry, why am I saying H? Lambda E by lambda P is equal to E divided by this thing, okay? So do you need to move that in square root everything? C is outside, C is outside, so let's keep C outside, move E inside the root, so that is equal to, then move E inside the root, So it will be E square divided by 2me, and they have written it raised to half, right, for square root. Then this thing gets cancelled out, so you have E by 2m raised to half, and there is c in the denominator, times 1 by c. It's 1 by c times of E by 2m raised to half. Okay, so that is option C, right? Okay, this is clear, everyone? Light of wavelength 500 nanometer is incident on a metal with work function of 2.28 electron volts. The de Broglie wavelength of emitted electron is, okay, yeah, so you will find out kinetic energy, right? Light of wavelength 500 nanometer is incident on a metal with work function of this much, 2.28 electron volts. The de Broglie wavelength of emitted electron is, simple. So just find out kinetic energy, and that is what it is, energy of a photon. Okay, so its wavelength is given, that means hc by lambda minus work function is phi naught. Okay, so put the values. What is hc? This is given in nanometers, so we'll make use of 1240 ev nanometer. Okay, hc is 1240 ev nanometer divided by, that is lambda equals to 500 nanometers minus phi naught is 2.28 electron volts. So what will be this thing? What I will do is I will multiply numerator and denominator by 2. So this is 1000, then this becomes 1000, right? And this will become what? 2480, and if I divide that by 1000, so it's 2.48. So 2.48 minus 2.28 electron volts, okay, that is 0.2 electron volts, but then 0.2 ev, and you have electron. Okay, so this thing can be written as p square by 2m. So this is kinetic energy of electron, and it can be written as E times V naught, right? V naught is the stopping potential. So if you need the stopping potential of V naught, right, to stop the electron, that means its kinetic energy must be equal to what? As if you can think as if it is accelerated by a potential difference of V naught. Okay, is this thing clear? Yes, no? Okay, and then you can just make use of lambda equals to 12.27 divided by square root of V, and in place of V we'll just put V naught. Okay, so that's 12.27 divided by root of 0.2, right? But what is square root of 0.2? So you can write this thing as 20 multiplied by 10 raised to minus 2 root of 20, so it's 4 point something. Okay, let's take 4.5. 4.5 multiplied by 10 raised to minus 1, take that 10 raised to minus 1 into the numerator, it becomes 10 raised to plus 1. Okay, 10 raised to 1, so this thing divided by 4.5, so nearly 3 into 10 raised to 1, 3 multiplied by 10 raised to 1 angstrom. Okay, so that is equal to, so it's 2.8 multiplied by something. Okay, so 3 multiplied by 10 raised to what? This is angstrom is 10 raised to minus 10, so this thing is 10 raised to minus 9 meters, or 3 into 10, sorry, 3 into 10 raised to minus 9 meters is 3 nanometers, right? So this is very round figure calculation. Okay, so now should it be less than or greater than that? So the answer is option D or option A. Tell me. it is accelerated by potential difference of, and this was maximum kinetic energy. Okay, that means velocity is maximum. If velocity is maximum means the wavelength is, that is the minimum wavelength. Okay, so that should be greater than or equal to, so it's option A. Is this thing clear, everyone? Then which of the following figures represent the variation of particle momentum and associated de Broglie wavelength? Tell me, which of the following figures represent variation of particle momentum and associated de Broglie wavelength? Yes, which one is correct? So option D. That's very simple, right? It's very simple. That lambda equals to, you have h by p, or p is inversely proportional to lambda. That's why option D. Okay, good. Let's see next one. The kinetic energy of particle is increased to 16 times its previous value. The percentage change in the de Broglie wavelength of the particle is, tell me. Kinetic energy is increased to 16 times the previous value. Percentage change in the de Broglie wavelength. Okay, so Ke prime is to Ke is equal to 16, right? So P prime, this is, okay, or let's take Ke2 is to Ke1 is equal to 16. Okay, so P2 square by P1 square, because kinetic energy is directly proportional to momentum square. So this is 16. That means P2 by P1 is equal to what? 4. Okay, so if P2 by P1 is 4, or 4 is to 1, I can say, then what would be wavelength? So the wavelength is inversely proportional to P. Wavelength is equal to h by P. It's inversely proportional to P. So if momentum becomes 4 times, wavelength will become what? 1/4. Okay, therefore you have lambda 2 is to lambda 1 is equal to what? It's equal to P1 is to P2. That's 1/4. 1/4 means how many percent? How much a percent? It becomes 25%, but that's not what they asked. The percentage change in the de Broglie wavelength. Okay, so what's the answer? Tell me. 75%, right? It's option B. Okay, it becomes 1/4 means lambda 2 is 25% of lambda 1, right? But if it is 25%, how much is the change? Change is 75%, right? Change is 75%. Good. Let's see next one. The wavelength lambda e of electron and lambda p of photon of same energy E are related by, tell me. Actually we had seen this. Energy is same. Okay, so energy of photon is equal to energy of an electron. So we can put the formula in terms of wavelength. So it is hc by lambda p is equal to energy of electron can be written as what? P square by 2 times its mass, right? And p is inversely proportional to lambda. P is equal to h by lambda. Okay, so let's put that. So you get h square by lambda of electron square times 2 times m, and this is hc by lambda p. Okay, then this h gets cancelled out with the square, right? And you can write this thing as hp is equal to lambda e square times 2 times m into c divided by h but all this is constant, right? All this is constant. So what you can say is lambda p is proportional to lambda of electrons square, right? Lambda p is proportional to lambda of electron square. It's option C. Okay, this is clear. Let's see next one. If the momentum of an electron is changed by p, then de Broglie wavelength associated with it changes by 0.5%. The initial momentum of electron will be. Okay, this is very simple. See, you have lambda equals to what? H by p. You have this formula, and what you are doing is changing the momentum of electron by p. Okay, momentum of electron is changed by p. Then its de Broglie wavelength changes by 0.5%. So here you can make use of again the first chapter, the delta lambda by lambda, right? Delta lambda by lambda is equal to what? It is equal to minus of delta p by p, because lambda is equal to some constant, that is h times p raised to minus 1, and that's why delta lambda by lambda is equal to minus of delta p by p, right? But then this change is 0.5%, so they are not saying increasing, decreasing, they are just saying that wavelength changes by 0.5%. So 0.5, okay, times of in denominator, what you can do is you can put wavelength equals to 100 only. Okay, so then what will be delta lambda? It will be 0.5 times of lambda, right? 0.5 times of 100. Okay, oh no, what did I say? All right, so let's do one thing. So this is delta lambda by lambda times 100 would be equal to minus delta p by p times 100. Okay, and this thing is equal to 0.5, right? Percentage change is 0.5. This is equal to 0.5, and then okay, but they are saying that momentum of electron is changed by p. So let's call the initial momentum as p naught. Okay, initial momentum as p naught, and change in momentum is delta p, so that you can call p then. Okay, so that's equal to p by p naught times 100 is equal to 0.5, and then you can move this thing on this side. Okay, so therefore what will you get? That initial momentum p naught is equal to 100 by 0.5 times of p. Okay, you can forget about the negative sign because they are just giving the magnitude, right? 100 by 0.5 is 200, so it's 200 times of p. This is clear? Yes, no? It's option A. Okay, everyone? Nikita, is it clear? All right, good.
Yes, sir.
Good. Let's see next one. Which one among the following shows particle nature of light? Tell me. Photoelectric effect. Yeah, photoelectric effect shows the particle nature of light. Good. And that's it. Okay.